Hello everybody, welcome to this summary series, and today we are going to discuss a very beautiful chapter of organic chemistry in class 12th, alcohol, phenols and ether. This chapter includes three parts. As I said, the first one is alcohol, then we have a ether or we can take a phenol, and then finally we will be ending up the discussion with the third part, phenol or ethers. So alcohol, phenols and ether, they all come from the same class of organic materials. They have oxygen common in all the three. So the first one, as I said, alcohol. Alcohol has oxygen. So these are the hydrocarbon containing compounds with a heteroatom. That heteroatom is oxygen. Then we have ethers. Ethers are also of the similar class, but instead of hydrogen we have R, another alkyl group, or we can have aryl group. Then finally we have a phenol containing phenol compounds. Phenols are benzene containing and then OH group present on it. So these are the three class of compounds we will be discussing in today's lecture, and let's start. So I welcome you all on this incredible station or incredible platform of PW, and I am your teacher Dr. Lakshya Kathuria, welcoming all of you to help in excelling, getting highest marks in your board examination, which you must have dreamed of that I would like to do, I want to do something different this year, right? So, all right, let's start with our chapter, everybody. We have three things to do: alcohol, phenols and ether. So the very first thing which we are going to discuss today, we will be trying to understand how to prepare alcohols. And then we'll discuss some of its reactions. After that, we'll discuss many reactions of ethers, which is one of the most underestimated compound in organic chemistry, ethers. Okay. And finally, we will jump on to its chemical properties, and we'll close our session by discussing lots of reactions of phenol. Phenol is very important. You'll see that how you find it in your daily life, right? I'm sure you must take green tea. Green tea, I am already before the start of the session giving you a question, what are the contents present in green tea? Okay. So obviously it has to be connected with the chapter. Either alcohol, phenol or ether is present in green tea. I want you to look through the Google and find out what is present and have to tell me in the comment box. Okay. As I discussed, these alcohol, phenol, ethers are hydrocarbon organic compounds, hydrocarbon, but they contain oxygen. So oxygen containing hydrocarbon. They contain oxygen as one of the hetero element. Now, alcohols can be categorized. Alcohols can be categorized into various categories. For example, the carbon that has oxygen attached to it based on its hybridization. It can be sp3, it can be sp2, it can be sp hybridized also. We'll look at all of them. Then we have a category based on the number of OH groups present. I can have one OH, I can have two OH, I can have three OH, I can have many OH. So monohydric, dihydric, trihydric and then polyhydric. Alright. Then we'll discuss vicinal dihaloid, the position of OH. If there are two OHs present, if they both of them are present on the consecutive carbons, carbon number 1 and 2, and if they are present on one after the another, I mean there is a gap in between, then we'll discuss also all these kind of categories. So let's start with our discussion for today. How I have planned this lecture for you, let me also tell you. I have designed this lecture in such a fashion that we will be having every single reaction which is included in your NCERT, also some other reactions, so that this particular lecture is going to be helpful for your board examination as well as NEET and JEE mains examination also. So you need not make any notes. You can just take a printout of the session slides that we are going to discuss today, and your short notes are ready. Your summary is ready. But every single reaction we are now going to discuss in detail. So alcohol, as we can said that, as I just said that we can categorize alcohol on the basis of the hybridization. Suppose I have CH3, CH2 and OH attached. So this carbon has got hybridization sp3. So how to calculate hybridization? Can you please explain us? Yes, you need to expand the molecule and count the number of sigma bonds and the lone pair present on particular atom of which hybridization you are looking for. So at this moment, I am trying to look for the hybridization of this carbon, which has one sigma bond here, another sigma bond, one more sigma bond, and one more. So how many sigma bonds do you see, guys? 4 sigma bonds. 4 sigma bond means what is the hybridization? It is sp3 hybridization. Is that clear, everybody, how to find out? Similarly, can you find out the hybridization of this oxygen? Yes, sir, there are 2 sigma bonds which are formed by oxygen, plus there are 2 lone pairs. So sp3 once again, sp3 once again. Remember, hybridization is of the central atom. It's not of the side atom. So if anybody asks, what is the hybridization of this hydrogen? No hybridization, right? Okay. So now I can have sp3 hybridized. I can also have sp2 hybridized. This is known as vinyl alcohol. This is known as vinyl alcohol. Although it is not that stable. Why? Because it undergoes an isomerism process known as tautomerism. And how does tautomerism happen? This group of hydrogen, it jumps over the second carbon to generate ketone or an alcohol. So it's carbonyl containing compound and alcohol. These two are isomer of each other. If you want, you can calculate the total. You can say that, oh, there is an extra hydrogen that I have here. So let me delete one hydrogen. This is one of the hydrogen that I have extra. Okay. So this was CH and then OH present. This becomes CH3, C double bond OH. Now the total number of carbon atoms are 1 and 2, 2, C2. Total number of hydrogen atoms 2, 1, 3 and then 4. How many oxygen atoms? Just 1. Let's check this also. How many carbon atoms? 1 and 2. How many hydrogen atoms? 1, 2, 3 and 4. And how many oxygen atoms? The ones again. So these two have the same molecular formula, but they have different their geometry, है ना, different connectivity. So such kind of molecules which have same molecular formula but different functional group, specifically when this hydrogen is jumping around, hopping around, this is known as tautomerism. This is known as tautomerism. This is one kind of isomerism and they both exist. That is a secondary question, sir. Which one exists more in amount? Which one is more stable? Generally, keto forms are more stable than enol. This is your en, this is your ol. So together it is enol. Right, everybody? That was second classification. Now I can have another one. For example, I can have CH triple bond C with OH. These are the categories which are rare. But anyways, for your satisfaction, you should know that this OH can also be present over here. Again, it can undergo tautomerism to form what? This hydrogen will be now having C double bond O. Understood? This is also possible. Why? Because this hydrogen will jump on this carbon and generate this molecule. Understood? Okay. This was the categorization on the basis of the hybridization of the carbon that has OH group attached to it. Now, the second kind of classification of alcohol can be, you have how many OHs present on the molecule. Suppose I have only one hydrogen, only one OH group present. This will be known as monohydric alcohol. Monohydric. Why? Because there is only one OH present. I can have a molecule with two OH present. Suppose this is the molecule that I have. Now, this will be known as dihydric molecule. This will be known as a dihydric molecule, right, everybody? Why? Because there are two OH present. Dihydric molecule, one example you should remember, this is known as ethylene glycol. Ethylene glycol. This is ethylene glycol. One, then we can have two, then we can have three. Suppose 1, 2, 3 carbons are attached with each other via single bond and each carbon has at least one OH present on it. This will be known as glycerol. This is known as glycerol. This is trihydric alcohol. How many how many OH molecules are there? How many OH functional groups are there, beta? 3 are present. Another classification of alcohol possible is if carbon has two alcohols, two OH group present on the two consecutive carbons, then this is known as vicinal dihalide. Vicinal diol, not dihalide, vicinal diol. If you have OH present, both these OH present on the same carbon atom, then this will be known as gem diol. Generally, carbon cannot hold two electronegative elements on it. For example, here both of them are OH. Oxygen is more electronegative element than carbon. This will immediately undergo dehydration and generate C double bond O. As a result of dehydration, there will be carbonyl compound generation occurs. All right. Okay. Now, as we have discussed what are the classification of these molecules, we need to understand their various reactions. So this is the way I have designed the lecture for you. I have brought this is how to be studied. The central molecule represent that these are the various reactions possible. So we will be starting making alcohols with the alkenes at the beginning. In the beginning, we will be using alkenes as the starting material to make to do various reactions, and the end product of all these reactions would be an alcohol. So I am going to take up these reactions on a separate slide, so that each reaction can be very well understood. So you can take a print of this. This becomes your mind map also. This becomes your summary slide also. Likewise, I have brought to you various reactions of alcohol, various reactions of ether, various reactions of phenols. Every single reaction from your NCERT is covered in this lecture. Every single reaction. So let's take this a general alkene ka formula and understand the very first reaction. Let's start from the left hand side. Let's number this is 1. Okay. What is this reagent? This is a tertiary butyl with C double bond C attached. So I am going to explain this to you. You have CH3 and another CH3 with CH double bond CH2. Let's go back and cross verify our structure that we had in the beginning. Is that right, everybody? We have tertiary butyl connected to carbon-carbon double bond. Tertiary butyl group connected to carbon-carbon double bond. Now what do we need to do? We need to add dilute H2SO4. Dilute, remember, it's a dilute H2SO4. Dilute H2SO4 is a source of H+, and water. Remember, acid will never ever come alone. It will always come with H2O. Once H+ comes, in my haloalkane haloarine chapter, I have explained to you, your job is to identify the electrophile and a nucleophile in a given reaction. I told you that the nucleophiles are having either absolute negative charge, or they have delta negative charge, or they have lone pairs, or they have carbon-carbon double bond, triple bond, benzene, etc. Right? Do you see that in this molecule there is a pi bond here? Pi bond makes this molecule a nucleophile. Is this much clear? Now, here you have hydrogen plus present, and the identification of electrophile is having absolute plus charge or delta positive charge or incomplete octet. Incomplete octet, right, everybody? Incomplete octet. Okay. This is the identification. So do I have a positively charged species here? Yes. So what is this pi bond going to do? It will attack on H+. So why not water? Yes, it has also happened. So first of all, let's try and understand why and how this reaction is happening. When I take a mixture of H+ and H2O, first H+ is the electrophile. If you understand this reaction, entire chemistry will be understood to you. That's my word to you. H+ finds that there is water also present. This is taken in one single reaction vessel. There are two lone pair present on the oxygen. This comes under the category of a nucleophile, and this comes under the category of an electrophile. Nucleophile attacks here, right? Now it generates H oxygen with a positive charge, right, everybody? And we know oxygen when it is neutral, and oxygen when it is positively charged. So electronegativity of oxygen positive is much higher than electronegativity of neutral oxygen. Neutral oxygen. This is of very great use in organic chemistry. We protonate an atom, we make it charged, positively charged, to increase its electronegativity to facilitate some reactions. Right? Now oxygen positive is going to take away the electrons from the nearby hydrogens. These three hydrogens are attached directly to it. What will happen? This hydrogen will try to give away the electron density via the sigma bond and generate a huge amount of delta positive charge. So this delta positive charge was here also, yes, but the amount of delta positive charge here is quite high, is much higher than the positive charge in neutral water. Is this much clear? Sure? Pakka? Now this pi bond says that if I am attacking on H plus or I am attacking on H plus here, basically H plus is never free. H plus is never ever free. H plus in water is always H3O plus, you should remember. I wanted you to understand that H3O plus is H plus source. H plus is not free. H plus is not free. H plus is connected to oxygen and now it is having delta, huge amount of delta positive charge. Now this pi bond is capable of attacking. Is this theory clear? Is this theory clear, everybody? All right. Now let's attack this double bond on H plus. This double bond attacks on H plus to generate CH3. There is a CH3 here also, CH double bond CH2 present. Now when it attacks on H plus, one of the carbon should obtain a positive charge. One of the carbon should obtain a positive charge. Either carbon number 1 or carbon number 2 should get that. So let's write both the possibilities. So CH3, CH3 and CH3. So CH, let's say the carbon number 1 gets a positive charge. So this becomes positively charged species and this becomes CH3. Clear, everyone? Okay. Now possibility number 2. There is a CH3OR, tertiary butyl group present. Suppose this time carbon number 2 gets a positive charge, so this becomes CH2 and CH2 positive charge. Out of the two, you need to find out which carbocation is more stable. How are you going to do that? Various possibilities. First one, aromatic effect. Aromaticity. If positive charge makes the molecule aromatic, it will be the best molecule ever. Second one, if aromaticity is not there, always check for resonance. And for resonance, what do you need? Pi bond. You need pi bonds. I am writing these effects in the sequence, in the order. If you mess up this order, your answer will also be messed up. So you first need to check for aromaticity. Second, you need to check for resonance. Third, you need to check for hyperconjugation structures. How many hyperconjugation structures are present? Then, fourth one, you need to check for inductive. If you check in a reverse or some other order, your answer will never ever match. Okay? Inductive, to stabilize carbon positive charge, I want plus groups present. We want electron donating groups present around carbon plus. Make sense, everybody? Are you with me? Okay. Now, here I see there is no pi bond, no aromaticity possible. Hyperconjugation, yes. Higher the amount of alpha hydrogen, more of the alpha hydrogen, higher will be the stability. Stability of carbon positive will also increase. Let's check for alpha hydrogens. This carbon plus, the neighboring ones are the alpha carbon, this also alpha carbon. Does this alpha carbon have any alpha hydrogen? No. Does this have? Yes. How many? 3. So 3 alpha hydrogen. Here, does it have alpha carbon? Yes. How many alpha hydrogen? Just 2 alpha hydrogen. Do you understand how to count? So out of the two, which one have higher number of alpha hydrogen? The first one. So should you make at all carbon number 2 this positive charge here? No, don't do that. Understood, everybody? Like, now from here, the first structure that is made, here, what you need to do is, what do you need to do after making carbon plus? Rearrangement. I see that if I move this CH3 here, this is known as methyl shift. With this pair of electron, I will pass on this positive charge to the neighbor carbon and generate a better stable carbocation. This is the positive charge satisfied by Again, look for all those stabilization effect. Is aromaticity there? No. Is resonance there? No. Is hyperconjugation there? Obviously, yes. This is my alpha carbon. This is also alpha. This is also alpha. So how many alpha hydrogens do you have? 3 from here, 3 from here, 6, 1 from here, 7. Anybody else? Is there any more alpha hydrogen? No. So 7 alpha hydrogen. This becomes my most stable resonance structure after, most stable carbocation after rearrangement. At this situation, I will bring water. Water was present, still waiting for carbocation to be generated so that it attacks. Now it will attack here. Final product generated would be tertiary butyl group. Instead of that, now you have CH3 and OH generated. Alcohol is made. Alcohol is made. Let's go back and verify. Is this our final compound? Is this our final compound? Let's check. Please go through once again. If you have not understood, please check this. Please listen to this once again, and we will be checking now. Did I write the right compound? Yes. Markovnikov addition. Don't go with this definition, guys. My humble request, my humble suggestion to you, do not go with just this blind definition. I don't like this definition at all. Why? Because this will always mislead you. Otherwise, you would have directly added hydrogen positive here, and OH negative here. Do you have that answer here? According to Markovnikov addition, we say that the positive part goes to the carbon having more number of hydrogen and the negative part goes to the carbon having less number of hydrogen. Is this the product here? No. OH is this present on the next carbon? Is hydrogen present here? Okay, yes, that's verified. Is OH present on this carbon? No. So don't use Markovnikov definition blindly. Always make the carbocation, then rearrange, finally make the compound. Is it clear? Boliye bhai, is it very clear? Is it crystal clear? Okay, done. So first one is done. Let's move to the second part. We have osmium tetraoxide. Osmium is one of the element which can tolerate 8+ oxidation state. 8+ oxidation state. So what's the structure of osmium tetraoxide, guys? ये है कुछ ऐसा. This side. This type of molecule it is. Osmium tetraoxide. Or we can have tetraacetate lead. Lead tetraacetate or tetraacetate lead it is. In presence of H2O2, what can we do? We can do gem diol preparation. I showed you in the previous slide, gem diol preparation can also be done when you bring in osmium tetraoxide. Now think very carefully. Osmium tetraoxide, let me introduce here itself. Osmium tetraoxide, carbon-carbon double bond. Carbon-carbon double bond, if it has to receive or if it has to come in contact with osmium tetraoxide, if it has to come in contact with carbon-carbon double bond. सुनना जरा, सुन लेना ध्यान से. This double bond moves here. This double bond moves there. What happens eventually? This is one vague way of understanding, hand waving argument here, that there will be carbon-carbon single bond and this oxygen forms a double oxygen forms a bond here. Another oxygen also forms a bond here. Osmium is hanging in between. These double bonds are also present over here. Do you see that the double bonds, the oxygens are being added from the same side? It's just like one pinch. If you want to hold something, you bring your index finger and thumb from the same side, right, everybody? So it's the same side. Osmium ka oxygens are biting the carbon-carbon double bond from the same side. They are biting it from the same side. So the product obtained in presence of H2O2 having OH and OH on both of these OH will be on the same side. This is known as syn addition. This is known as syn addition. Syn means the same side. Understood? Same side. Clear, everybody? All right. You can also use lead tetraacetate in place of osmium tetraoxide. But you should understand why is it syn compound? Why is it syn addition? Understood? Why is it syn addition? Don't go with the product that are made over here. If you are confused, just you need to check whether it is all preparation or not. You might see that there are some time differences between this group and that group. It's okay. Yeah? You can just make that change if you want, but don't be confused. I'm already telling you that this group, sometime you will see that I have written it as CS3 for in the interest of space. Otherwise, you can make a modification. This is CCH3 whole thrice. CCH3 whole side, tertiary butyl group present over here. Understood? Okay. Now we have a reagent called KMnO4. Everybody knows KMnO4 is an oxidizing agent. But when we take it in the dilute condition and cold, dilute conditions does not oxidize the molecule that greatly. So what it does instead, it will rupture the pi bond. It will rupture the pi bond. Carbon-carbon double bond, hydrogen, hydrogen, KMnO4 in cold and dilute condition will oxidize both these carbons by providing OH and OH. It again forms a diol, KMnO4. This is known as Bayer's reagent. क्या बोला जाता है? Bayer's reagent. Very important. Sometimes you will not see that it is written as KMnO4. Rather, they say that the carbon-carbon double bond was treated with the Bayer's reagent. What will be the product? The product obtained is diol. What kind of diol? What kind of diol, guys? Vicinal diol. All right. Okay. Then we have again syn addition. Remember again syn addition. So there are various ways of adding, making diols, and how do we make that? These are the possibilities, plus anti and syn addition can be also maintained. So far we have discussed syn addition of carbon-carbon, syn addition of OH-OH across carbon-carbon double bond. Let's look at some other parameters, some other reactions also. Let's name this reaction as reaction number 2, which is known as hydroboration oxidation. Hydroboration oxidation. One of my favorite reaction. Hydroboration oxidation reaction. I myself have done this reaction approximately 500 times in the laboratory. Very interesting reaction to do. Let's understand what is this reaction. Basically, B2H6 molecule, I want you to pay attention first. I want you to tell me what is this molecule called? BH3. BH3 is known as borane. BH3 is known as borane. Very good. What is the nature of this molecule? Is it an electrophile or is it a nucleophile? What is it? Do you see any positive charge? No. Do you see any negative charge? No. Do you see delta positive charge? No. Do you see delta negative charge? No. Do you see pi bonds? No. Do you see any sort of function group present? No. Then what's the nature of this BH3 molecule? There is a hydrogen present, hydrogen and hydrogen. There are 1, 2, 3, 4, 5, 6 electrons present around boron. And if you remember, one of the identification of electrophile is that incomplete octet. This boron does not have 8 electrons with it. 8 electrons are not at all there. Rather, it has just 6 electrons. Just 6 electrons. So it's desperately looking for 2 more electrons to fulfill its deficiency. 2 more electrons to fulfill its deficiency. So what happens at this stage? BH3, one borane molecule, knocks the door of another borane molecule and say, Baba, give me 2 electrons. The borane who had opened the door, he says, no, 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 you are asking the wrong question. This is my question. This is my dialogue. Baba, give me something. Give me 2 electrons so that we two can share, we two can help each other. But then this guy is asking electron to another borane. And this is also asking another borane for the same question, same number of electrons. So who is going to help each other? They actually help each other. They actually help each other by forming such kind of molecule. I'm sure you have seen this, you have studied this in your grade 11, group number 13, chemistry. Do you remember this molecule? Have you seen this anytime? This is known as diborane. This is known as diborane molecule, right? But my question, everybody, hydrogen having just 1 electron, how is it managing to form 2 bonds? Hydrogen has just 1 electron, how is it forming 2 bonds? To form a bond, you need an electron, right? Huh? To form a bond, you need two electrons. This boron has got its electron here, 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 here. These are the three electrons of boron also which are shared. Boron also does not have any other electron to share with hydrogen. What is happening here? क्या चल रहा है ये? What is going on? Here also boron is sharing two of its electron with two of these hydrogen and the third one with this hydrogen. There is absolutely no electron here, absolutely no electron here. How did this bond form, guys? Tell me, how did this bond form? Kaise? How? How is this bond formed? I will tell you very important point now. You must have heard about coordinate bond. You must have heard about coordinate bond. Now there are various kind of coordinate bond can be formed. Array sir, various kind of coordinate bonds. We have just learned one of it. Array, if you have a pair of electron, if you have pi bond, if you have sigma bond, all these can form coordinate bond. So we have seen only the lone pair forming coordinate bonds. Pi bond can also do that. Sigma bond can also do that. But sigma bond is used at last. At last. If none of these are present, sigma bond is present and you want to make a coordinate bond, then you have to make it. You have to use it. Abhi kya hua na? What has happened here? This is sigma bond, this is also 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 sigma bond. Now boron says, bhaiya, can you offer me one of your sigma electron so that I can complete my octet? It says, okay, let's do that. It says, but you also have to do the same. Okay, do that. And eventually you make this molecule look like this. But the reality is this. The reality is B2X ka molecule is this, but here we draw it for our simplicity just to say that hydrogen is forming bridge between the two hydrogen. Actually, this pair of electron, this orbital is forming bond with the empty orbital of boron. The sigma orbital, sigma bond is forming bond with the empty p orbital of boron. This is the theory behind it. And this is known as a 3-center 2-electron bond, and that bond, if it is facing each other, if there are two such kind of bonds present, then it is known as banana bond. Then it is known as banana bond. Why is it called a banana bond? Because the shape of the orbitals bent a little bit and then therefore they get shape of banana, which looks like banana. So the banana bond actually is this. These orbitals, they bent in such a shape that it gets banana kind of shape. This has to be banana bond only when there are two such 3-center 2-electron bonds are present. If there is only one 3-center 2-electron bond is present, will it still be a banana bond? No. Okay. Now, why I wanted to discuss this in much detail? Because B2H6 molecule is of very, very poor stability. It reacts with water. Wow. It reacts with water. Boom, boom. It reacts with oxygen again. Boom, boom. Lots of energy produces. Why? Because they are going to now get electron pair which are of much lower energy. They are going to get electron from pair of hydrogen from this oxygen, they are going to obtain the electrons from here. Why to use very, very, very low energetic pi electrons? Why to use that? Are you following me? If you have B2H6 molecule made, and from outside there is water present, why do they actually going to form? Why are they anyways going to form this coordinate bond which is made up of sigma electrons? If from outside the electrons from oxygen are available, this will immediately break it. They will be immediately rupturing of this dimer, and they will produce monomer once again, BH3. Sir, if electrons from lone pair can do that, can pi electrons can also do that? Yes, CH2 double bond CH2 can also break this dimer. Understood? All right. So we have now come to our background that if you bring CH2 double bond CH2 and if you bring B2H6 breaks into BH3 and they start interacting by making some sort of intermediate. Some sort of intermediate. One of the boron interacts with one carbon, hydrogen interacts with another carbon. This double bond breaks here, this pi bond breaks here. So this pi bond breaks, sigma bond forms, sigma bond breaks, sigma bond forms. So what you are going to get eventually? CH2, CH2 has received another hydrogen and it has BH2 unit present on it. Do you see that, guys? What has happened? We have broken BH bond and then formed this molecule. Now when I react it with H2O2 in the presence of basic medium, this bond is so much labile, it breaks nicely. Once it breaks, you will obtain CH2, CH2 with the hydrogen and obtained alcohol is obtained. Is that point clear? This is one of the premium method, one of the best method of producing alcohols. Since I have not at all talked about carbocation formation over here, so you do not use Markovnikov rule. Never ever, don't use that. So if you want to use, then use anti-Markovnikov rule. Anti-Markovnikov rule will be followed in hydroboration oxidation. Let me explain why the name. So hydroboration has happened here. Hydroboration of this carbon-carbon double bond has happened over here. Then oxidation has happened over here in the presence of H2O2 basic medium. Let's come back and see if we have done what we were desiring to do. See this? We take B2H6 in THF. What is THF? Tetrahydrofuran. That's one of the cyclic ether. That's just a solvent here. Nothing else. No other role for it. No other role. Just a solvent. THF, tetrahydrofuran. Then basic medium and H2O2 together will produce an alcohol. Do you notice there was a carbon-carbon double bond? I could have introduced OH here or OH here. According to anti-Markovnikov rule, the negative part of water, basically it is hydration. The negative part of water, that's OH minus, and positive part of water, that's H plus, will go to the carbon like this fashion. Negative part goes to the carbon having more number of hydrogen. Hydrogen plus will go to the carbon having less number of hydrogen. That's anti-Markovnikov rule. Is this clear, everybody? Bata do yaar. Is this clear? Anti-Markovnikov rule is followed. This is a brilliant, jitna bolu kam, brilliant method to prepare terminal alcohols. Terminal alcohols. Sir, are these mechanisms important? Yes. Yes, they are important. 100% they are important. Otherwise, you will just try to memorize organic chemistry, and memorizing organic chemistry is a crime. Remember, it's a crime. Okay. Police aayegi, police leke jayegi. The next reaction is known as, this reaction is known as oxymercuration, demercuration, OM-DM reaction. Very important once again. You can directly go by the definition. Here, only this particular reaction, you can just go by the definition of Markovnikov rule. Hence, there is no carbocation generation. There is no lafda of any sort of carbocation rearrangement. Done ho gaya? Pakka? Sure, everybody? The next reaction is very important. I am going to discuss that once again with the help of epoxidation reaction. So, suppose you have carbon-carbon double bond, and then what do we need to do? What are the reagents, everybody? You need to understand the reagents properly. There is RC triple bond, RCO3H. Okay. I am having C double bond O, oxygen, and H. This is known as peracid. This peracid is an oxygen donor. It's nascent oxygen donor. Nascent oxygen. Very reactive. Very reactive. What is it going to do? It will get inserted between carbon-carbon double bond. There was a CH2 here, there was a CH2 here, and that gets inserted like this. This molecule is known as epoxide. Industrially very important molecule. Epoxides. Now when I bring in H plus, what is this H plus going to do? H plus will be attacked by this oxygen. See, I have just identified there is hydrogen plus electrophile and a nucleophile present here. These two are going to react with each other. It will form CH2. CH2, oxygen. Two bonds were already formed. Now third bond has formed, so oxygen must get a positive charge. Understood? Earlier, due to this oxygen, this carbon was experiencing some delta positive. This was also experiencing same amount of delta positive charge. But here the amount of the delta positive charge is increased. Here the amount of delta positive charge is increased. Since both of these carbons are similar, I can choose any one of it and attack by water. Attack by water. There will be H2O. Suppose I want to just attack on one of these oxygen. Let's say, okay, fine. We will proceed like that. So it attacks on this carbon. Once it attacks on this carbon already has 1, 2 from hydrogen and third from this carbon, fourth from this oxygen. 4 bonds are made. Fifth one, it refuses immediately that I cannot form 5 bonds. Carbon says I just can form 4 bonds. From childhood, I have been making just 4 bonds. So how come in my budapa, in my Javani, I am going to form more than 4 bonds? So this carbon double bond, this carbon-carbon bond, carbon-oxygen bond opens up. You will obtain H2O here with a positive charge and there is OH present. Do you see that I have made OH on the opposite side? Both the opposite side, yes, because it is purely SN2 attack, and SN2 attack happens from the backhand side. Now you have to remove H plus that you had used in the beginning. H plus will be lost. It will be CH2, OH here, and then CH2 with oxygen OH here. This makes a molecule diol. Diol, but anti-addition. This is known as anti. Many people call it as an anti. I also like to call anti-addition. Anti-addition. So what we have discussed, guys, we can prepare carbon-carbon OH, right? If you want to get the syn compound, syn diol. If you want to get syn diol, use what? Use osmium tetraoxide, or you can use lead OAC. OAC क्या होता है? What is OAC? Acetate. Acetate. You can use that, or you can use for syn diol once again KMnO4. Bayer's reagent. Bayer's reagent. Bayer's reagent. बात समझ में आ रही है? Everybody, are you following? बोलो. Then you have anti or syn diol, or we can say it's anti syn or anti addition, anti diol. Anti addition can be done via epoxidation. Via epoxidation. Clear? Chamka? Okay, next. Let's go to our another kind of reaction. Okay, this is done, that is also done. I'm giving you one question. You can halt it for a minute, you can pause it for a minute. I want you to answer this question, everybody. You can check in the comment section. I will also come and check after the session. Suppose I give you this molecule. Dilute H2SO4, reaction number 1. Then HgOAC whole twice. That's reagent number 1. That NaBH4, reagent number 2. Okay. Product number 2 here. Then okay, then okay, 1, 2. Okay. Reagent number 1, B2H6 taken in THF. You can take help from your notes, everybody, and then answer in basic medium with the help of H2O2. With the help of H2O2, basic medium. OH minus. Okay. Product number 3. I want you to find out the product number 1, product number 2, product number 3, and write down there IUPAC naming in the comment box. IUPAC naming in the comment box. I'll come and check. Right, everybody? Okay, let's move. My guarantee to you guys, this is going to be one of the question in your board examination. This is 100% going to come in your boards. Fine. Let's move to some more properties, some more methods of preparing alcohols. Some more methods. Okay. We have now alkyl halide. If I treat it with Ag2O, moist Ag2O, remember moist Ag2O is a source of moist Ag2O is viewed as AgOH. It's a source of OH minus. Source of OH minus nucleophile. So alkyl halide will be immediately attacked by aqueous QH or moist Ag2O. Both of them essentially mean the same thing. The product obtained is methanol or alcohol in general. Alcohol in general. Now, when alkyl halide CH3Br is reacted with magnesium, it has to be taken in dry ether. Why do we need dry ether? Because this will be generating methyl bromide. Methyl bromide magnesium. This is Grignard reagent. Do not call it Grignard, please. G is silent. Grignard reagent. You'll be surprised to hear that I am very much fond of, I am so much fascinated with Victor Grignard, sir. What he had done in chemistry for us. You can actually make any compound using Grignard reagent. I have his picture in my room hanging on the wall. Whenever I wake up in my morning, I say hello to my parents and say hello to Victor Grignard. Right, everybody? Okay. Now, dry ether is used to make CH3MgBr. This is a very powerful nucleophile. Powerful nucleophile. Powerful nucleophile. Okay. What is it? Why is it powerful nucleophile? Because CH3 is supposed to have a negative charge here. Huge delta negative charge here. Huge delta negative charge. This becomes a powerful carbon containing negatively charged species are powerful nucleophiles. They can also act as a base though. Base, or they can act as a nucleophile. If this CH3 is attacking on H+, it can form CH4. This H+ can be source of H+ from any compound. It can be from acid, from alcohol, from phenol, from anything. Or it can attack on carbon delta positive charge. Then it will form carbon-carbon single bond. This becomes a foundation of entire organic chemistry. What do we do in organic chemistry? We make carbon-carbon bonds. So this becomes important molecule to do, to make carbon-carbon double bonds. So what are we going to do? We will be discussing various reactions starting from Grignard reagent. Let's take first of it, attack on epoxide. So I have CH3 minus. From now onwards, I'm just going to take CH3 minus. CH3 minus, when it attacks on this epoxide, I told you this oxygen has electronegativity nature. It will generate a delta positive charge here. This attacks here and this ring opens up. Once this ring opens up, you will obtain CH3. Always number these carbon atom. Number 1, this is number 2, this is number 3. So carbon number 1 and carbon number 2 have formed bond. And carbon number 3 has oxygen minus attached to it, which will be satisfied by MgBr next to it. Mg is going to carry positive charge. Once you add water, in the end of any reaction of Grignard reagent, you will be adding water for sure. So that to finish the reaction, to complete the reaction, to end the reaction, there is a technical word used known as quenching of the reaction. Quench karte hain. We quench the reaction. Quenching, we add water. This bond will be formed now. What is this molecule going to be called? CH3, CH2, CH2OH. This is an alcohol we intended to make. Understood? So reaction number 1 is done with the help of epoxide. Check please. Now we are going to do a reaction with an ester. So what do we do with an ester? Okay. Now we have a CH3 minus attacking on CH3 C double bond O OET. What is ET? Ethyl. So मैं खोल के लिख देता हूँ. Ethyl. CH3, CH2, CH3. CH3 minus comes and attack on the center. This group leaves and you will obtain CH3, a ketone. CH3, C double bond O and CH3. This is acetone. If you want, you can stop the reaction here. If you want, you can carry it forward. You can react this acetone product obtained with another molecule of Grignard reagent that is going to attack over here. This bond will open up. Final compound obtained will be CH3 with oxygen minus CH3. Now it's understood to you, sir, in the end, are you going to add water? Yes. Once you add water, it becomes H, alcohol. What is the nature of this alcohol? Primary, secondary or tertiary? It's tertiary alcohol. Tertiary alcohol. So can I say that using Grignard reagent with an ester, you can make tertiary alcohols, or you can stop it at ketone by controlling the amount of Grignard reagent added. Clear everyone? Okay. Chaliye, let's go back. See, I have made ketone and then finally tertiary alcohols. Clear honi chahiye guys baatein. Now you can use Grignard reagent, which is CH3 minus, can attack on oxygen also. Once it attack on oxygen at 60 degrees, and when you do in a protic medium, the compound obtained is always methanol. Very powerful method of preparing methanol industrially. Now, the similar reaction can be observed here. This was my methyl ester. This is the ester here. Instead of that, I have here another type of ester. So the compound obtained here, so we had here CH3. Instead of CH3, let's take hydrogen. What is going to happen? CH3 minus plus H, C double bond O, ET likh raha hu, I am writing ET. So this CH3 attacks over here, this group leaves, and the compound obtained is hydrogen, C double bond O and CH3. Do you see that's an aldehyde? Bolo bhai, it's an aldehyde. You can stop the reaction here by adding water, or you can continue with another equivalent of Grignard reagent which attacks here. C double bond O opens up, you'll obtain OH by adding water. Obviously in the end, hydrogen, CH3 and CH3. What kind of alcohol it is? Secondary alcohol. Did you follow everybody? Is that clear? Let's go back and check if we intended to make secondary alcohol. Yes, we have done that. Clear everyone? Sure everybody? Okay. Now we have another sort of epoxide. Earlier we had simple epoxide, simple. So these two centers were symmetrical, but here it's not symmetrical. Remember, when you have unsymmetrical epoxide, the CH3 minus will always choose to attack on less hindered site. So it is going to attack over this carbon center. So carbon number 1, carbon number 2, carbon number 3, carbon number 4. So from left to right, carbon number 1, 2, 3, 4. So the carbon number 1, 2, 3. This will have OH. OH is present over here. Now you can write the name of the molecule, starting the numbering from here. 1, 2, 3 and 4. Did you understand everybody? If you have unsymmetrical epoxide, always choose to attack on the less hindered carbon of the epoxide carbon ring. Okay. These were the methods of preparing alcohols. Few more reactions of Grignard reagent. So I'm going to explain it here. Let's react CH3 minus with another sort of an aldehyde. Earlier we had formaldehyde. Now this will attack to form CH3CO minus, which will be neutralized of course later, and you obtain a secondary alcohol. Check please, you have obtained secondary alcohol. I am sure you guys are following. Okay, now let's take just formaldehyde. If I take formaldehyde, what's going to happen? CH3 will attack, CH3 minus attacks on H, C double bond OH, and you will generate HOH, primary alcohol. Wow, primary alcohol is obtained. Clear everybody? This is very important reaction. I would like to go on the next page to explain it to you. How do we actually make this molecule? We have CH3 minus again, loads of reaction. You will be seeing, sir, is it so many reaction possible by Grignard reagent? Yes, that's the reason I pay him so much of gratitude every morning, because I'm in love of organic chemistry that is made by Victor Grignard. Great man, great man. Now CH3 minus comes an attack on this C double bond O, and Cl leaves, because Cl is a leaving group. It leaves in the form of Cl minus. You obtain CH3, C double bond O, CH3. That's your acetone. It can be further attacked by, further attacked by Grignard reagent, that's CH3 minus, it comes here, forms a tertiary alcohol. Tertiary alcohol is obtained. Clear? Okay. Let's go back to our another reaction that we need to see. See, this tertiary alcohol is obtained. Are you following? Now you can start with the ketone. We have also seen that ketones will also give you the tertiary alcohols. Clear? आगे बढ़े. Shall we proceed? Okay, awesome. Awesome, blossom. Now, some of the properties of alcohol. Likewise, we will be discussing ether, we'll be discussing phenols. So you need not open your NCERT at all after this session. You just have to watch this for a couple of times and you're done, right? Okay, you start from an alcohol. The alcohol can be converted to alkyl halide. We also discussed this reaction in alkyl halide chapter also. So when you treat ROH with SOCl2, you will be converting it into RCl, and the side product obtained are SO2 and HCl. Remember, SO2 is a gas and HCl is also gas. Is HCl a gas? Sir, I have seen HCl kept in a bottle. In my laboratory, in my school laboratory, HCl is kept in a bottle. Why? You are saying HCl is a gas? Arey, HCl is a gas, re baba. Why? Because in your laboratories, you have HCl dissolved in water. It's just like another soft drink, CO2 dissolved in water, HCl dissolved in water. Don't drink that. But HCl, if you keep the bottle open for some time, HCl is evaporated, HCl is gone, HCl has escaped the water layer, and it's just the water which is left after in the laboratory. So this becomes an extremely it's an excellent method of producing alkyl halide, as there is no further purification of the product obtained here is required. The other products, the side product obtains are the gases. So they will escape the reaction vessel, and according to Le Chatelier principle, from chemical equilibrium perspective, if the reactants are converted to product and you want to push the reaction in the forward direction, one way of pushing it into forward direction much more and more by taking out the reaction, taking out the products obtained here. So product are escaping, SO2 and HCl are escaping, and the result obtained is just RCl. Okay. You should know what is the mechanism. Does it follow? It's SN1 mechanism. You can also treat it with SOCl2, but in the presence of pyridine. This is known as pyridine. You should know that pyridine, which contains nitrogen, it's a base. It's a base, it's bad for men. Nitrogen containing bases, nitrogen containing compounds are bad for men. So for example, this is bad for men. Okay. I am just telling you, bad for men. And sulfur containing compounds are bad for women. This is known as pyridine. Many people call it as pyridine. कुछ भी बोलिए, उसको कौन सा सुनाई देता है, pyridine or pyridine. In this particular mechanism, there will be an inversion happening. Inversion of alcohol. If you start from a chiral version of alcohol, the compound obtained will be inverted. So SN2 mechanism, it follows SN2 mechanism. Remember pyridine. कैसे याद रखें? How to remember? Pyridine has I inversion, I inversion. Pyridine I pyridine I say inversion. Okay. Again, the product obtained are H2, SO2 and HCl. But here you will be having retention. Here you will be having retention plus inversion, because it's an SN1 reaction. But if you want to have 100% inversion product, what you are going to do? You will be adding a few drops of pyridine, and you are through, you are done. Yeah, alcohol can also be treated with HX. Then you will obtain this compound haloalkanes. Haloalkanes can be made by secondary and tertiary. They follow SN1 mechanism. We know that secondary and primary will follow SN2 mechanism because of its steric crowding behavior. I would like to introduce one more reaction here, one more test here for an alcohol, that's known as POC, practical organic chemistry test. So if you react an alcohol, that's ROH, if it is reacted with ZnCl2 in presence of HCl, concentrated HCl, so ZnCl2 plus HCl combination is known as Lucas reagent. Lucas reagent. Treat both of them together, the compound obtained is RCl. Plus, there is zinc compound obtained, that would be zinc ZnOCl. This is the compound of zinc obtained, which is of white PPT. white color PPT. Generally, it is not soluble in water. So, if it is your primary alcohol, then you need to use ZnCl2 and heat it also. Without heating, this reaction won't work. This will take long time. This will take long time for the turbidity or the milkiness to obtain. Turbidity to appear. This is practical test to appear. If you have secondary alcohol, now treat it with ZnCl2, no need of heating. ZnCl2 and HCl, it will take approximately 15 minutes for turbidity to appear. Understood? If you have a tertiary alcohol, you need not heat it. Also, you need not use ZnCl2. You can just go with HCl and the turbidity will form immediately. Immediately turbidity will obtain. Thus, this becomes a practical organic test for the primary, secondary and tertiary alcohols. So how are you going to distinguish between the two? Between the three, you just have to use ZnCl2 and HCl Lucas reagent. If turbidity appears immediately, it's tertiary alcohol. If it takes 5 to 15 minutes, it is secondary alcohol, and if it takes longer time and you have to heat it also, then it is primary alcohol. Clear, everyone? Okay. Now, if you treat it, let me come on this side. If you treat it with PCl5, then the product again obtained is alkyl halide. You can treat it with PCl3. Compound obtained again will be, let's say, chlorine here. This is chlorine. The compound obtained will be again alkyl halide. You know, the trick that board examiners they use is they ask you what is the side product. The trick that JEE mains and the NEET examiners they follow is they will ask you the side product of this reaction. So POCl3 is the side product obtained. What happens to phosphorus? This is what they are going to ask. And what happens to phosphorus here? So this forms H3PO3 molecule. Do you notice that out of 1, 2, 3, 4, 5 chlorine, PCl5, only 1 chlorine is getting installed in this alkyl halide molecule. Rest are wasted. So this 3 are wasted here, plus one more thing will be formed, that's HCl. HCl will also be formed. So 4 chlorines are wasted. But here in this molecule, I am seeing that all the 3 are used to make alkyl halide. So do you think this becomes more atom economical method where you are not wasting any chlorine atom? Correct? Good. Awesome. You can also react with PBr3, cousin of this PCl3. You can also react with PI3 and you can form your corresponding bromo and iodo compounds. So out of all of these, the best method to make alkyl halide from alcohol is SOCl2 treatment, thionyl chloride treatment. Right. Let's discuss some more reactions of alcohol. So there are so many reactions. Yes, organic chemistry reading from NCRTs will be just a reading. It will never be an understanding. So you need to just get these notes ready. Then you read NCRT, keep the two things parallelly, keep the two things alongside, and then make sense out of every single sentence written in NCRT. It's written in compact way, nothing else. So when you treat this an alcohol with concentrated H2SO4, what you need to understand, dilute H2SO4 is a source of H+, concentrated H2SO4 is a dehydrating agent. It's a dehydrating agent. If you understand the role of reagent, you will be able to do reactions also. It's a dehydrating agent. What does dehydrating agent do now? It will try to remove water. It will dehydrate, obviously. So concentrated H2SO4 or concentrated H3PO4, both of them are going to do the same thing. The compound obtained will be having loss of OH and hydrogen from here, and a double bond is formed. So the compound obtained will follow even mechanism. Even mechanism means via carbocation formation, and that carbocation will be undergoing rearrangement. Remember, it will undergo rearrangement for sure. Then they will be ZZEF rule or SETZEF according to SETZEF or ZZEF. Same name, same cheese hai ye, same cheese. SETZEF alkene will be formed. What is SETZEF alkene? The one which have high alpha hydrogen. High alpha hydrogen around carbon-carbon double bond. carbon-carbon double bond. Clear? Now, if you take P2O5 and heat it, Al2O3 heated, phosphorus pentoxide or alumina heated, the compound obtained will be always gaseous in nature. They ask you these questions in your boards as well as in JEE mains and NEET examination. They ask you how many gaseous products are formed. Then you need to say that P2O5 will work at heating condition. Alumina will work at heating condition and the compound obtained will be according to Setzeff rule. But here comes that if you just heat an alcohol above 400 degrees Celsius, that temperature, your compound will be dehydrated and product will be Setzeff once again according to Setzeff. Thorium oxide heating, POCl3 heating. These are the two most ignored reactions. So I have brought to you so that you need not check where these are written in NCERT. So here it is. So they two are both dehydrating agents and produce a product according to Hoffman mechanism. And all the four follow E2 mechanism. Understood everybody? They follow E2 mechanism. Clear? आगे बढ़े? Okay. Now let's do some more reactions of alcohol. How can we oxidize alcohol to a higher oxidized compounds? है ना? Oxidation करना है. So carbon which is having oxygen, what is the oxidation state? Can you tell me in the comment box, everybody? What is the oxidation state of carbon containing alcohol group? What is the oxidation state? What is the oxidation state of carbon here? And now I oxidize it to RC double bond OH. What is the oxidation state here? I further oxidize it to C double bond OH. What is the oxidation state of carbon in each cases? Tell me. Done? Calculated. This is carbon with a +1 charge. This carbon is carrying 2+ charge. This carbon is 3+. So do you see that? So this is continuously undergoing oxidation. Yes, it is undergoing oxidation. It's undergoing oxidation. And there are reagents which are going to help us in making these oxidized compounds. So from an alcohol, you can oxidize it to carbonyl containing compound. From carbonyl, you can further oxidize it to carboxylic acid. If you want to prepare carboxylic acid, you need strong oxidizing agent. For example, KMNO4, alcoholic KMNO4. Do not get confused with Bayer's reagent. That was cold and dilute KMNO4. Here it is alcoholic KMNO4, which is purple color nature. You can oxidize an alcohol, that's primary, to its sodium or potassium salt, depending potassium salt of the acid obtained. The compound will be asked to you, or the statement will be given to you, will be the following, that a primary alcohol was treated with KMNO4 and the purple color is discharged. What is the product obtained, which is brown in color? The compound obtained is manganese in 4+ oxidation state. It's a redox reaction. Manganese is in 7+ oxidation state. So this 7+ is reduced to 4+, manganese is reduced. Oxygen is oxidized from 1+ to 3+. Okay? Very good. So purple color discharges, so this becomes one of the tests of checking whether there is alcohol also present or not. So alcohol can be oxidized, purple color will be discharged. Remember, KMNO4 can also oxidize olefinic double bond. Like I told you, Bayer's reagent can also oxidize carbon-carbon double bond into diols. Okay, we can use acidic K2Cr2O7, which has an orange color. Upon oxidation of an alcohol to acid, strong oxidizing agent, the green color compound obtains. Green color compound has chromium in 3+ oxidation state. Remember, some colors I want you to remember. I am so much into inorganic chemistry. I love to remember their colors. I love to ask colors. So this way I will help you in understanding color or the compounds also. Chromium 3+, green. Chromium 6+, orange. Orange in color. Sometime you will see that chromium 6+ will be in red color also. For example, chromyl chloride. Okay. Now there is another reagent called Jones reagent. Jones reagent will oxidize. It's a combination of CrO3 in aqueous H2SO4. Again, oxidation happens up to the acid. If you use PCC, PCC is pyridinium chlorochromate. Pyridinium chlorochromate. Now when nitrogen is protonated pyridinium chlorochromate, then you can oxidize this molecule. You can oxidize this molecule to alcohol to, this is pyridinium. This is with a positive charge. Now fourth group is present, pyridinium. PCC will oxidize it to just an alcohol. Remember, from here, these are going to be weak or mild oxidizing agents. So they are mild, and above this line, above this demarcation, they are strong oxidizing agent. If you want to stop up to the alcohol, up to the aldehyde formation, you need to carefully choose what reagent will be useful to you. You can also use PDC, pyridinium dichromate. You can also use just copper. These all are the questions are asked in the examination. So I have prepared this slide just for your convenience, guys. So copper can be used, and you need to heat it approximately in between 300 to 400 degrees Celsius. And then the compound obtained will be RCHO. And then once again, let me see if I can take this. Yeah. I am sure now you are able to see the screen from the bottom, which was cut earlier. This is Collins reagent. What is Collins reagent? Collins reagent is CrO3, mild once again, CrO3, and we have to use DCM, dichloromethane, DCM is dichloromethane. In presence of pyridine, once again, this combination is known as Collins reagent. Again, the product obtained will be just an aldehyde. Clear, everybody? Okay. Okay. Now we have a molecule which is known as ether. All these reactions of alcohols are done or understood. Now we need to know what are ethers, and we have looked at ether functionality, that carbon oxygen carbon functionality is known as ether. If you have it in an open chain, that's simple, and if you have in a cyclic compound, that is cyclic ether. For example, THF, tetrahydrofuran. Let's learn how to make them first, then we will discuss their chemical properties also. So how do we make ether? Let's start with ethanol. If you heat ethanol in presence of, this is important question, guys, please note it down, this is important. Ethanol, when heated in the presence of H2SO4, approximately at 140 degree, you need to remember this temperature. JEE mein, there was this question asked once, at 140 degree, what do you obtain? Do you obtain the dehydrated product, that is CH2, double bond CH2, or do you obtain an ether? The answer is ether. You obtain ether, particularly at 140 degree, ether is obtained. Make sense? Clear, everybody? Please keep this in mind, that at approximately 140 degree, ethanol can be converted to this ether. Diethyl ether, diethyl ether. This is known as diethyl ether. You can start with ethyl iodide, treat it with dry Ag2O. Silver is going to take up the iodide, and carbon-carbon bond formation occurs, and this oxygen starts sitting into between this carbon-carbon. So this will be C2H5 iodine goes away, oxygen comes, another C2H5 molecule forms diethyl ether once again. Now when you treat it with alcohol, when you treat an alcohol with diazomethane, let's discuss that. CH3, you have diazomethane. Diazomethane is CH2 negative diazomethane. Okay. And triple bond nitrogen. There is a positive charge. Correct, everybody? This is diazomethane. Diazomethane. Very important molecule industrially. This negative charge attacks on this hydrogen. What does it form? It will immediately generate CH3, CH2, oxygen negative, and plus CH3, nitrogen positive, triple bond nitrogen. Due to this nitrogen, there is a huge delta positive charge on this carbon, and this oxygen immediately attacks here, and nitrogen also leaves. This is an excellent leaving group. So CH3, CH2, oxygen, CH3 with nitrogen gas liberates. This is your ether form. So if you want to convert an alcohol to its methylated ether, then the best method is to use diazomethane. Okay, let's go back. You can also treat it with a molecule which is CH3CH2I. How are we going to do that? Let's discuss that. This is known as Williamson synthesis. Williamson ether synthesis. Williamson ether synthesis. Very important. From your board's perspective, very important. They will ask you to write few things about what is Williamson ether synthesis mean. So we will be using RONA, sodium salt of an alcohol, and reacting it with alkyl halide. I have made it R dash just to distinguish between the two. This RO minus is going to attack via SN2 mechanism so that this X leaves. Upon X leaves, there will be ROR bond formation. Now this is my alkoxide. Alkoxide. This will be alkoxide. Alcohol forms alkoxide. Alkoxide. ROR dash. Alkoxide forms. This is the alkyl halide. You can choose any alkyl halide with any alkoxide, sodium alkoxide, to make your own wished compound, wished ether. Oxygen, carbon bond can be formed. So in this particular example, we have, this is the alkoxide. So this negative charge species will attack on this molecule. X leaves. So CH2, oxygen, CH3. This will be the compound obtained. Again, diethyl ether is obtained. This is a very important reaction. Treating it with mercuric acetate, what will happen? The ether will form upon treatment of an alkene with it. So ether can be also obtained. Remember, if you use methanol, if we use ethanol as a solvent, you can also use this. You can also use this method, taking carbon-carbon double bond and alkene, treating it with an alcohol in the presence of H+. They will be, let me do that example also for you. So starting from CH2, double bond CH2, these all examples are very important, guys. So let's react it with H+. What's going to happen? So you have in the beginning these two molecules. So you will be having on the side, let's say ROH. In general, ROH reacting with H plus will generate ROH positive. This carbon-carbon molecule, carbon-carbon double bond is going to eventually attack on this carbon center to generate CH2 with CH, oxygen. This molecule is one possibility that this reaction can occur this way, or what you can do instead of that, we will be protonating to make our compound of interest. We will be just protonating first my alkene, so it generates a CH3, CH2 positive. Now this alcohol molecule will attack on this center and generate CH3, CH2 and OR with H with a positive charge, and then proton loss in the end will generate R, oxygen, CH2, CH3. The ether is formed. So remember, first you have to protonate your alkene, then there will be carbon, the oxygen bond formation happening. Okay? Okay. Let's see if there is anything else left over here. No, nothing. So this preparation methods of ethers are also discussed. Let's discuss some of the properties of ether. Very important. You can take this a snapshot. You can take it as it is. If you react carbon, oxygen, carbon, this is known as alpha carbon, reacted with X2 in dark. Very important, guys. This X gets installed here. One of the X gets installed on this alpha carbon and on the other side of alpha carbon. So compound obtained will be X here, oxygen and X here. Remember, only one alpha hydrogen will be replaced from both the ends, from both the sides. But if I treat it with X2 in the presence of light, entire molecule ka hydrogen will be replaced by chlorine or halogen that you use. See this, entire hydrogens are replaced. Okay, substituted basically. If you react ROR with HCl, what are going to make? R, oxygen, positive charge, R, there is hydrogen here. Now Cl minus is also present. Cl minus attacks on the center. This leaves and RCl forms. This will leave and RCl form. And RCl will form. So the compound will generate ROH plus RCl. See this, guys, they will be ethanol formed plus they will be RCl formed if you treat it with HCl. But this reaction, I want you to focus on this particular reaction first. This reaction, guys, this is very, very, very important. If you treat CS3 with CS3COOL, let's say I have R oxygen R with R C double bond O Cl. This is my lone pair present on the oxygen. They will attack over here and this Cl will lost. Cl will be lost. So R C double bond oxygen and the compound obtained will be having this molecule, and one of this R group will be taken care by zinc. So basically what we can write, there is ZnCl2 present here. There is a ZnCl2 present here. So I will be bringing ZnCl2. One of the chlorine will be taken up by the R group of the ether. The mechanism is a little complex. So I am trying to make you convinced that this OR molecule goes and sits here. The other R forms RCl. The two compound are formed. One of it forms alkyl halide, the other one forms an ester. Clear, everybody? Okay. Okay, this is done. Right. Now some more properties, chemical properties of ether. You can react your ROR with under extreme heating and aerobic conditions. You have to heat it under oxygen. You can oxidize the entire molecule. This is basically your combustion reaction, right? Combustion, converting carbon into CO2 and water, and H2O is also formed. I want you to answer what will be the physical state of this molecule. You have to write down in the chat box what will be the physical state of H2O under combustion reaction. Under combustion reaction. Combustion reaction. Write down in the comment box what is the physical state of H2O you expect under combustion reaction. Again, dilute H2SO4. You should remember that ROR upon treatment with H plus, they will be attacked by this oxygen pair. This becomes ROR with hydrogen and a positive charge. Now comes water. Water is a nucleophile. As I told you, dilute H2SO4 is a combination of oxygen positive and water. Water attacks on the center and alcohol forms. Alcohol forms, another alcohol forms. If both of these are same, so both the sides will have same alcohol made. Hence, there is 2 here. So which acid will give you the best method, best yield? HI, because HI is the best acid among HX, right? Now, if you use it HI under cold condition, then you obtain the alkyl halide and alcohol. You do not get 2 kind of alcohols here. Remember, this is very important. This reaction we also study. This reaction will also study that HI upon heating, cold condition, these are the product. HI under heating, under excess condition, these are the 2 alkyl halide compounds obtained. Alkyl halide. This bond ruptures. This bond breaks. This bond actually breaks. This bond breaks from here, and both these RR partners, they will receive halogen. They will receive halogen. And what is the halogen in HI? Iodide. Now PCl5 or POCl3, we know this will also be converting. This ROR upon treatment with PCl5 will also showcase similar reaction as of an alcohol. So compound obtained will be RCl. RCl is the answer. These were the reactions of ether. Now let's talk about phenol. Phenol is the most interesting among alcohol, phenols and ether. I know these are going to be too much reactions for you, but this has entire NCERT, maybe a little beyond of that, right? Okay, so phenol, how do we make phenol? We can start with the sodium sulfonated ring, benzene ring. This is sodium sulfonic acid ka sodium salt. When you fuse it with NaOH, what does NaOH do? It will remove sulfonic group from benzene ring, and then you will obtain OH. Phenol, direct method, nice method, very good method. Number 1. Diazonium salt reaction. These are various repeated reactions. Diazonium salt upon treatment with water, you have to just warm it. You will obtain phenol as the product. This is known as a decarboxylation reaction. This is also heating in the presence of soda lime. Calcium oxide, when you heat in the presence of NaOH, you can get rid of this C double bond O H group. This is salicylic acid. You can make just phenol from salicylic acid by heating it in the presence of NaOH and calcium oxide. This guy is known as cumene. This guy is known as cumene. Cumene in the presence of oxygen will produce cumene hydrogen peroxide. Upon acid treatment, you can get phenol. Very important method. Very, very, very important method. On the right hand side, you can start from methyl. You have phenyl magnesium Br. Phenyl means pH and Mg with a positive charge. Now, when you react it with oxygen, as I told you earlier, we have discussed this reaction. This is going to produce pH, OH upon addition of water in the end, basically. pH, OH. This reaction is a heterogeneous reaction. Chlorobenzene, you can treat it under these heterogeneous conditions. You can produce phenol. This is Dawes process. We study this Dawes process in haloalkane, haloarine chapter also. You can start with the chloro and then treat it with OH minus NaOH and it can be replaced. But this reaction is although very tough because of double bond character between chlorine and the benzene ring. This is an important reaction which makes it important on itself. Why? Because hydrogen of benzene ring is not very reactive. So you can still oxidize it. You can insert oxygen here in the presence of V2, vanadium pentaoxide, V2O5, vanadium pentaoxide. This was the question asked in JEE once. This will be asked in your board also. You can write it down. Okay, now let's discuss some more preparation methods of properties of phenol. If you start with the phenol and treatment in the presence of Br2 water, this is Br2 water, bromine water. Bromine water, what is the color? You have to answer in the chat box. What is the color of bromine water, right? You will get 2,4,6 tribromophenol, multi-substitution, all the ortho positions and the para position, everything will be substituted. But if you do that reaction in the non-polar solvent like CS2, you will obtain para as the major compound. These ratios also I am going to recommend you to remember. 93% of bromo compound, para compound and just 7% of ortho compound obtained. You treat it with concentrated H2SO4 at 100 degrees Celsius. To be particular, remember 100 degrees Celsius, you will obtain there will be two ortho, one of the ortho and one para position will be substituted. Treatment under this condition, NaOH and Br2 condition, you will obtain Br on this position, on the ortho position and OH remains. This is desulfonation method. You can remove sulfonic groups also. Now, treatment under HNO3, this is nitration condition. Nitration condition will also nitrate one of the leftover position here, that's nitro position, and treatment of with the further higher amount of or higher condition of nitration, you can replace all of these. You can just get rid of all these sulfonic group and place NO2, NO2 and NO2. Trinitrophenol it is, trinitrophenol. On the left hand side, now it is on my right hand side, treatment with the concentrated HNO3 and H2SO4 will produce trinitrophenol directly. You can either go it this way or directly you can produce this. Alongside you get some oxidized product, hence the yield of this reaction is much lower. You can treat it with NaNO2 in the presence of H2SO4, you will obtain nitroso, para-nitroso compound, which upon treatment with phenol and H2SO4 you obtain blue-green compound. Adding water, you get red color. Adding NaOH, you get blue color. Again, this was the question asked many times. This has been asked many times, that what happens after what? Once you add phenol and H2SO4, there is a blue color, blue-green color. Then what do you add so that the color changes? H2O in excess, so that this will be excess. This will be excess, not that excess, red color, and then add NaOH to form blue color. On the other hand side, nitro can be oxidized to NO2 upon treatment with HNO3. This is very important slide, everybody. You can just try to see how much of diversity these phenol reactions can be done. This is the last for today. So phenol can be reacted with formaldehyde in methanol. You obtain para or ortho product. Upon treatment with NaOH, you obtain one of the polymer known as bakelite. Bakelite is a thermosetting plastic which upon heating can just die. It's a thermosetting. It cannot be used anymore. Then we have chloroform and KOH treatment. This gives you carbene as the reagent, carbene as the intermediate form, CCl2, and the product obtained is orthoformylated phenol. Orthoformyl. This is salicylaldehyde. The name reaction, this is a name reaction, Reimer-Tiemann reaction, very important. You can treat it with HCN and HCl so that you can obtain para product in the major, para product major using Getterman reaction. If you want to obtain ortho product major, you have to do Reimer-Tiemann reaction. This is important. If you react phenol with phthalic anhydride, there will be phenolphthalein generation. Phenolphthalein, this is a test for it. For the presence of phenol, pink color compound obtains in the presence of NaOH. When you add NaOH, then you get pink color. In the neutral condition, there will be absolutely no color to phenolphthalein obtained. On this side, when you treat it with CO2 and NaOH mixture, you can get a salicylic acid. At 125 degrees, ortho is the major product, but at higher temperature, para is the major product. Remember these two temperatures specifically. You can directly use CO2 and KOH. Again, you will obtain this compound. Similar reaction, just similar reaction, CO2 KOH, CO2 NaOH. Ortho is the major compound. When you use NaOH and this is benzene diazonium salt, there will be dyes formed. These are diazo, colorful dyes. Diazo dyes. Colorful dyes due to extended conjugation. Treatment with acetone, what happens here? Acetone is CH3, C double bond O. So from this side of phenol, I have taken the hydrogen. Suppose there was a hydrogen here. From this side also there was a hydrogen here. So HH and oxygen, water elimination and carbon-carbon bond has formed. I am sure you have understood what is this going on here. So hydrogen of the phenol, para position of the hydrogen, para position hydrogen from phenol, para position hydrogen from another phenol, and acetone molecule is C double bond O. Dehydration happens under concentrated HCl condition. You obtain this molecule. These are the few tests of or few properties of phenol that we had to discuss today. So I am giving you few questions to practice at home, everybody. First, this. So they are important for your exam perspective, for your board exam perspective. I want you to try them and post the answer in the comment box. That's it for today, everybody. And I hope this session and these slides are useful for your board examination as well as for your upcoming NEET and JEE examination. Also, we will discuss many more reactions in the upcoming sessions. Hopefully, they will be easy now to understand since you have understood the logic, the fundamentals of organic reactions. Now, we just have to look for an electrophile and nucleophile and attack the two to form a covalent bond between the electrophile and nucleophile. This is your teacher, Dr. Lakshya Kathuria. I hope you have enjoyed today's lecture. I'll see you in the next class, guys. Till then, goodbye. Stay safe.